In this video we look at an important property of the roots of quadratic equations. We know that the roots or the solutions of a quadratic equation can be found using factorization, but we also know that not all quadratics will factorize easily. They can be found using the method of completing the square, or they could be found using the quadratic equation formula. This formula is actually useful because if we look at the value of b squared minus 4ac, that is the discriminant of the quadratic equation, then if b squared minus 4ac is positive, it's greater than 0, then the equation has two distinct real roots. If b squared minus 4ac equals 0, the equation has one real root, which is repeated. And if b squared minus 4ac is less than 0, the equation has no real roots, but it does have two complex number roots. And you may have already met complex numbers. If you haven't, you will certainly meet them later in your study of the FM1, the Further Maths Unit 1. So let's have a look at a few quadratic equations, all of which we can solve at this stage. So x squared plus 9x plus 18 equals 0 will factorise as x plus 3, x plus 6 equals 0. So that gives me x is either minus 3 or minus 6. So the roots of this equation are the numbers minus 3 and minus 6. We're going to evaluate the sum of the two roots and the product of the two roots in each case. So in this case here, we've got alpha plus beta is just minus 3 plus minus 6, which is minus 9, and alpha times beta is minus 3 times minus 6, which is 18. The equation 3x squared minus 5x plus 2 equals 0 will also factorise as 3x minus 2 times x minus 1 equals 0. So I've got solutions of x equals 2/3 or x equals 1. So the roots are 2/3 and 1. The sum of the roots is 2/3 add 1, which is 5/3. The product of the two roots is 2/3 times by 1, which is 2/3. The equation x squared minus 4x minus 9 equals 0 doesn't factorise, but we can solve it using either the quadratic equation formula or by completing the square. I've chosen to do it by completing the square. So x squared minus 4x is the same thing as x take away 2 squared, take away 4. We've still got the minus 9. So altogether I've got x minus 2 squared, take away 4, take away 9 equals 0. Tidy that up. I've got x minus 2 squared equals 13. So x minus 2 is plus or minus the square root of 13. So x must be 2 plus the square root of 13, or 2 minus the square root of 13. So my two roots are 2 plus root 13 and 2 minus root 13. If I add those together, the root 13 simply cancel each other out and we get 4. To find the product of the roots, I'm going to have to do a little bit of multiplication of surds. So I've got 2 plus root 13 times by 2 minus root 13. That gives me 4, take away 2 root 13 plus 2 root 13 plus minus root 13 times root 13, which is root 13 squared, which in other words is just 13. So in that calculation there, the minus 2 root 13 and the plus 2 root 13 cancel each other out. 4 minus 13 gives me minus 9. For the equation x squared plus 10x plus 25 equals 0, I've got a factorisation of x plus 5 times x plus 5 equals 0. So I have got a repeated root of minus 5. So the roots in this case are minus 5 and minus 5. The sum of the roots is minus 10. The product of the roots is 25. If I've got the equation 2x squared plus 12x plus 18 equals 0, I can divide that equation through by 2. I've got x squared plus 6x plus 9 equals 0, which factorises as x plus 3 times x plus 3 equals 0. In other words, I've got a repeated root of minus 3. So this has got roots of minus 3 and minus 3. The sum of the roots is minus 6. The product of the roots is 9. Looking at these results, what we're going to be trying to do is find a connection between the coefficients of the original quadratic equation and the values of alpha plus beta, the sum of the roots, and alpha times beta, that is the product of the roots. So, what we've got here is the table from before, and I've just pulled out the coefficients. So the coefficients of the equation x squared plus 9x plus 18. A is the coefficient of x squared, which is 1. B is the coefficient of x, which is 9. And C is the constant coefficient, which is 18. Now what we're trying to see is whether there's any connection between the values of alpha plus beta and alpha times beta with the values of A, B and C. So let's start off looking at alpha beta. Can we see a pattern between the answer to alpha times beta and the coefficients of the original equation? So for the equation 1x squared plus 9x plus 18 equals 0, where a equals 1, b equals c, b equals 9 and c equals 18, we had alpha times beta equals 18. For the next one, we had a is 3, b is minus 5, c is 2, and alpha times beta was 2/3. For the next one, we had a is 1, b is minus 4, c is minus 9, and we had alpha times beta was minus 9. The next one, we had a is 1, b is 10, c is 25, and we had alpha times beta was 25. And for the final one, we had a was 2, b was 12, c was 18, and alpha times beta was 9. Now it doesn't take too much to note that the value of alpha times beta certainly doesn't seem to have very much to do with the value of b, but is very closely related to the values of c and a. And looking carefully, I'm hoping you might spot the fact that alpha times beta is actually equal to c divided by a. Just check that through on each of the values. And we need to try and do a similar sort of thing, see whether we can spot a pattern between the value of alpha plus beta and the values of A, B and C. Now in this case you'll probably spot fairly quickly that the value of alpha plus beta doesn't have very much to do with C, but is closely related to A and B. And with that little hint, I think you'll fairly rapidly get to the fact that alpha plus beta is minus b over a. Now let's see whether we can explain these two results. So let's suppose that the equation ax squared plus bx plus c equals 0 has got roots of alpha and beta. Well, that certainly means that the equation that x minus alpha must be a factor of ax squared plus bx plus c, and x minus beta must be a factor of ax squared plus bx plus c. So I must have ax squared plus bx plus c having a factor of x minus a factor of x minus b, but there's also going to need to be a numerical factor of a there simply to get the coefficient of x squared working correctly. If we now multiply out the right hand side, we get ax squared plus bx plus c on the left hand side equals a times x squared minus alpha x minus beta x plus alpha beta. In other words, I've got ax squared plus bx plus c equals a times x squared minus a times alpha plus beta times x plus a times alpha beta. And if we compare the coefficients, first of all, if we look at the coefficients of x on the left hand side, we've got b. The coefficient of x on the right hand side is minus a times alpha plus beta. And if we look at the constant coefficient on the left hand side, we've got c, and the constant coefficient on the right hand side is a times alpha beta. Dividing the first of these equations by minus a gives me minus b over a equals alpha plus beta. And dividing the second of these results through by a gives me alpha times beta equals c over a. So we've just proved the two results that we spotted in the previous slides. So if we've got the equation ax squared plus bx plus c equals 0 has got roots of alpha and beta, then we know that alpha plus beta must be minus b over a, and alpha times beta must be equal to c upon a. So for our first example, we're told that alpha and beta are roots of the equation 5x squared plus 7x minus 3 equals 0. Without finding the values of alpha and beta, we've got to determine the values of, first of all, alpha plus beta. Well, we know that alpha plus beta is equal to minus b over a. A is the coefficient of x squared, in this case 5. B is the coefficient of x, in this case 7. So minus b over a is minus 7 over 5. Alpha times beta, we know, is equal to c upon a. C is the coefficient of the constant. It's the constant number at the end of the quadratic equation. So c is minus 3. So alpha times beta is c upon a, which is minus 3 over 5, or minus 3/5. The next part requires us to calculate the value of alpha squared plus beta squared. Well, alpha squared plus beta squared is closely related to alpha plus beta all squared, but we know that alpha plus beta all squared is alpha squared plus 2 alpha beta plus beta squared. So really we need to get rid of that 2 alpha beta that we've got to make the algebra correct. So alpha squared plus beta squared is exactly the same thing as alpha plus beta all squared, take away 2 alpha beta. Alpha plus beta all squared is minus 7 over 5 squared, and then 2 alpha beta is 2 times minus 3/5. So what we've got there is 49 25ths plus 6 over 5, which gives me 79 25ths. For alpha cubed plus beta cubed, we can do a similar sort of thing. We can say that alpha cubed plus beta cubed is going to be closely related to alpha plus beta all cubed. We need to have a think about the expansion of alpha plus beta all cubed. So if we think about Pascal's triangle for a moment or two, we should be able to remember that alpha plus beta cubed is the same thing as alpha cubed plus 3 alpha squared beta plus 3 alpha beta squared plus beta cubed. So alpha cubed plus beta cubed is going to be the same thing as alpha plus beta all cubed, but we need to get rid of the 3 alpha squared beta and the 3 alpha beta squared. The terms that we're getting rid of have got a common factor of alpha beta, so we can rewrite this as being alpha plus beta cubed minus 3 lots of alpha beta times by alpha plus beta. Now we know the value of alpha plus beta is minus 7/5, and we also know the value of alpha beta is minus 3/5. So we've now got alpha plus beta cubed, alpha cubed plus beta cubed is the same thing as minus 7/5 cubed minus 3 times by minus 3/5 times by minus 7/5. Minus 7/5 cubed is minus 343 over 125, and 3 times minus 3/5 times minus 7/5 is 63/25. And that ends up giving me minus 658 125. 1 over alpha plus 1 over beta. Well, we're adding two fractions, so the sensible thing might be to write it in terms of a single fraction by using a common denominator, and the common denominator is going to be alpha times beta. 1 over alpha is the same thing as beta over alpha beta. 1 over beta is the same thing as alpha over alpha beta. So 1 over alpha plus 1 over beta is the same thing as beta plus alpha over alpha beta. We know that beta plus alpha is minus 7 over 5. We know that alpha times beta is minus 3 over 5. So that gives me minus 7/5 divided by minus 3/5, which is 7 over 3. And finally, for this question, we've got alpha over beta squared plus beta over alpha squared. A similar process can work. We can write the addition of the two fractions as a single fraction. If we introduce a common denominator, the common denominator is going to be beta squared alpha squared. Alpha over beta squared is the same thing as alpha cubed over beta squared alpha squared. Beta over alpha squared is the same thing as beta cubed over beta squared alpha squared. So we've got alpha cubed plus beta cubed over alpha beta all squared. We know that alpha cubed plus beta cubed is minus 658 over 125. We know that alpha beta is minus 3/5, so alpha beta squared is going to be 9/25. So the top of the fraction is minus 658 125. The bottom of the fraction is 9/25, and that ends up giving me minus 658 45. Our second example, we have the equation x squared plus 5x plus 3 has got roots alpha and beta, and without finding the values of alpha and beta, we've got to find a quadratic equation which has integer coefficients whose roots are 3 alpha minus 1 and 3 beta minus 1. We're going to tackle this question in two different ways. The first way is making use of our work on the sum and the product of the roots. So we certainly know that alpha plus beta is always equal to minus b over a, and we know that alpha times beta is equal to c upon a. So for this particular question, we've got alpha plus beta is equal to minus 5 over 1, which is minus 5, and alpha times beta is going to be c upon a, which is 3 upon 1, which is 3. An equation whose roots are 3 alpha minus 1 and 3 beta minus 1 will be the equation x, take away 3 alpha minus 1, times by x, take away 3 beta minus 1 equals 0. That certainly has got solutions of x equals 3 alpha minus 1 and x equals 3 beta minus 1. If we multiply that out, we get x squared minus 3 beta minus 1 times x minus 3 alpha minus 1 times x plus 3 alpha minus 1 times 3 beta minus 1 equals 0. And if we then collect together the x terms, that's going to be x squared minus, now I've got 3 alpha plus 3 beta, take away 2 lots of x. And then the constant term is the same thing as 9 alpha beta minus 3 alpha minus 3 beta plus 1. Now, 3 alpha plus 3 beta minus 2 is the same thing as 3 lots of alpha plus beta, take away 2. I know that alpha plus beta is minus 5. So that's 3 lots of minus 5, take away 2, which is minus 17. And 9 alpha beta minus 3 alpha minus 3 beta plus 1 is the same thing as 9 alpha beta, take away 3 lots of alpha plus beta, add 1. I know that alpha times beta is 3. I know that alpha plus beta is minus 5. So that can be rewritten as 9 times 3, take away 3 times minus 5, add 1, which is 27, minus minus 15, add 1, which is 43. So the equation I have got is x squared minus minus 17x plus 43 equals 0, or more sensibly, x squared plus 7x plus 43 equals 0. Now there's a completely different way of answering this question. Okay, so we've got exactly the same question. Okay, and all we're going to do is we're going to introduce a new variable, we'll call it y, which is equal to 3x minus 1. If y is 3x minus 1, that's the same thing as saying that x is y plus 1 over 3. We know that the equation x squared plus 5x plus 3 equals 0 has got roots of x equals alpha or x equals beta. Now we're going to rewrite the whole thing in terms of y's. So every time that x appears, we're going to replace it by y plus 1 over 3. So the equation y plus 1 over 3 squared plus 5 lots of y plus 1 over 3 plus 3 equals 0 has roots y plus 1 over 3 equals alpha or beta. Just doing a little bit of algebra on both parts of that statement, we can rewrite the equation part by expanding y plus 1 over 3 squared to obtain y squared plus 2y plus 1 over 9. Expanding the 5 times y plus 1 over 3 to obtain 5y plus 5 over 3. And then we've got the add 3 equals 0. So the equation has become y squared plus 2y plus 1 over 9 plus 5y plus 5 over 3 plus 3 equals 0. Has roots. Well, if y plus 1 over 3 equals alpha, then that means that y plus 1 is 3 alpha. In other words, y equals 3 alpha minus 1. And similarly, if y plus 1 over 3 equals beta, it means that y must be 3 beta minus 1. Now the equation that we've got there is rather messy at the moment, but it can be tidied up by multiplying through by 9. If I multiply through by 9, I'm going to get y squared plus 2y plus 1 plus 9 over 3 times 5y plus 5, which gives me 15y plus 15, plus 9 times 3, which is 27, must equal 9 times 0, which is 0. Tidy that equation up, we've got y squared plus 17y plus 43 equals 0, has got roots of y equals 3 alpha minus 1 or y equals 3 beta minus 1. So we've got two different approaches to the same question. Okay, to finish with then, here is a similar looking question. What I'd like you to do is just pause the video, have a go at this question using one or other of the two methods, and once you've got an answer for the question, restart the video and see whether your answer resembles my solution. You'll find that I've done the solution using both methods. All I want you to do is use one or the other of the two methods at this stage. So here's a solution if you've used the alpha beta method of going through, and you should have ended up with an equation looking something like x squared minus 16x plus 49 equals 0. If instead you decided to use method 2 and you started off by letting y equal x plus 2, then you'll have gone through and you'll have ended up with the quadratic equation y squared minus 16y plus 49 equals 0. Really doesn't matter whether the final answer is given in terms of x's or y's, it's the quadratic equation that matters. And that brings us to the end of our work looking at the roots of quadratic equations.